So thank you, and welcome to all of you. The event's about to start. So, as part of Polar Oceans Day here at the Christfield Pavilion, we're now going to begin our event, Multiple Threats to Polar Oceans. So, thank you to the pavilion organisers for inviting us, and to Plymouth Marine Laboratory for organising the event too. We've got a really good program this morning. We've got an excellent panel, some online, some in person. Just to briefly introduce myself as moderator. So I'm Matt Frost, and I chair the UK's Government Marine Climate Advisory Body. And it's interesting because in 2019, I remember when we had the SHROP, the Ocean and Cryosphere report came out, and I was tasked with helping the UK government write a response to this. And the ocean bit was fine, but then there was the cryosphere bit, and there was the question: well, is this completely relevant to the UK? We're not in the polar areas. It became very obvious when you looked at what it was being said that yes, it's totally relevant, not just to the UK but the entire planet. To sort of pinch a phrase, what happens in the cryosphere doesn't stay in the cryosphere. It's really important for everybody. So yeah, we helped draft that response, and you can really see we're going to hear a bit about it from Helen Finley and others in a while, but you can really see that from the recent report. So that was 2019. We just had the most recent 2024 report from the ICC, and they're clearly saying that on the trajectory we were on, 2 degrees, possibly even 3 degrees, we're going to see billions of dollars of damage. We're going to see billions of people affected and impacted. So even though the discussion today is on the cryosphere, polar oceans, actually this is incredibly important for the entire planet. So it's so good that you're all here to be part of this event. As we go along, please get your questions ready for the panel as a whole or individual panelists. We've got a really good panel. I'll introduce them as we go along, but really without further ado, the people you really want to hear from are our panelists. And we're really honoured as our opening speaker to have, I'm going to try and pronounce your name correctly. Huge apologies if I don't get it right, but Paul Ungaut. Yes, okay. Who's from the Inuit Circumpolar Council, Canada. He's Vice President of Nunavut Incorporated. And he's going to be our opening speaker. We then are going to be followed by a few online. And thank you, those of you who are online, because I understand the time zones are crazy for these guys. So they're going to follow up afterwards. But without further ado, can I invite Paul to talk about the ICC Canada perspective on the importance of polar oceans and the implications of a change in Arctic. Over to you, Paul. Thank you.
Is that, you just speak like this? Okay, good. Hey, look good. Queen Lemig for inviting me here to speak on behalf of Nunavut Inuit and its delegate to the Inuit Circumpolar Council. I appreciate Matt Frost for inviting us and the fellow panelists for spotlighting the vital role of the polar oceans. The Arctic Ocean is more than just water and ice for us. It's our home, our culture, and our lifeline. The ice is our infrastructure. It's our highway, not just for Inuit, but for our animals as well. For Inuit, the ocean provides food, connection, and the foundation of our life. When we talk about triple threats, acidification, warming, and freshening, we talk about change that impacts every part of our world. These changes aren't just distinct risks. They are here now, affecting us every day. And if you look at the ice in the Arctic, when I was growing up, when it started to melt in the springtime, there would be three things that would happen. The water would form in the top, but the ice would be very thick. And then the water would disappear, and the ice would still be very thick. Then you can travel on it. And then the ice would start to open up cracks. And finally, the ice would thin down and break up. That's what used to happen. Today, we get water, and all of a sudden, it just starts breaking up. The ice starts breaking up. That's what's happening today. So what's happening is that our oceans is getting warmer through acidification. It's eroding from the bottom. So when we get snow melt in the springtime, it breaks up right away because it's so thin now. So that's what's happening. Our traditional knowledge, give us a deep understanding of these shifts. Paired with modern science, we are rapidly seeing changing Arctic. This combined knowledge tells a powerful story. The Arctic is in crisis, and so are we. The Arctic warming is disrupting ecosystem and food webs, shifting species that our communities have relied on for generations. In fact, we're starting to see more and more southern species coming up. Because one of our elders said, when you start seeing changes like global warming, most of the southern animals will start coming up north to get away from the heat. Because not only our oceans are warming, our earth is warming. That's why we're seeing more and more forest fires. That impacts the ice. So we're seeing both effects in the Arctic. Hunting and fishing patterns, once reliable, are now uncertain, affecting not just food, but our cultural identity. Fresh water from melting ice is altering ocean circulation and weather patterns beyond the Arctic, with far-reaching consequences. Coastal erosion threatens our homes, because if you look at Nunavut, we got 25 communities, and most of them are in the coastal areas except for one. So it's affecting our homes because they're built very close to the sea. So it putting us in a position where our culture is threatened, a possible loss of life. So that's what is happening with the warming of the ice. So at COP29, we must remember that reducing emission isn't optional. It's essential to survive. For us, the 1.5 degrees target is more than just a goal. It's a lifeline. Every fraction of a degree makes a difference for Inuit, Arctic biodiversity, and the stability of the global climate. Our ice is melting faster than anticipated. Warmer, acidified water disrupts life cycles. And the changes we are seeing are too rapid for even resilient communities like ours to adapt. We need urgent global action. Reducing emissions protects not only Inuit communities, our way of life, but also our ecosystem and economics worldwide. Economies worldwide. We need our stewards of the Arctic lands and oceans, guided by sustainability and respect for all life, not just Inuit, but our wildlife. We invite partners with non-Arctic nations that respect and amplify Inuit knowledge and practices, supporting Inuit-led conservation, resilience, and youth initiatives benefits the Arctic and provides lessons for sustainable oceans management everywhere. The Arctic is sending warning signals. Ice melt, warming waters, acidification. We're not passive observers. We are defenders of this planet. We ask you to stand with us to protect our oceans and safeguard the future for all. Thank you for listening, and I look forward to continuing our dialogue together. Even though this is a very noisy event, I hope you can hear me, and I hope our voice isn't drowned out. Thank you.
Yeah, what's the thank you, Paul. That was excellent. And you're right, there may be some noise here, but in terms of your message, we really heard you. And you know, I love hearing from people who, I mean, I'm kind of scientist, and you know, I'm used to dealing with figures and words on the page, but to hear from somebody who lives this, who this is an observable reality day to day, is really powerful for all of us. So thank you so much. That was great. We're now going to move to our online speakers. So we have some very senior and high-profile scientists who are really experts in this area. I would say if you want to move, well, I don't know if there is anywhere to move forward. Maybe move your chair forward a little bit. Hopefully you can hear this clearly. But I'll introduce each scientist one by one as they give their talks. And I should say once again, thank you so much to the three of you, because I know you're all in different time zones and there's all sorts going on. So yeah, to drop everything and come and speak to us at COP, it's a real honour for you to have that, for us to have that. So thank you so much. So our first speaker is Professor Helen Findlay, who's a senior scientist at Plymouth Marine Laboratory. Helen is also Executive Council member for the Global Ocean Acidification Observing Network. And Helen is going to speak to us on state of the polar oceans and connections with the broader cryosphere. So Helen, over to you. Thank you.
Thank you, Matt. Hopefully you can hear me okay. It was really lovely to hear from Paul, and I think that's a really nice way to set the scene, because obviously Paul and the Nunavut and the Inuit communities are living this experience, and we're a bit more removed as scientists from the kind of generic academic world. So it's a hard one to follow when you've got someone who's actually living this experience. But what I want to do is the ICCI release every year a cryosphere report. As part of that, we have a polar ocean chapter. And this is a bit of information I want to give about 3 of the threats facing the polar oceans, giving a little bit of an update, but just general kind of overview of where we are in terms of those threats from a scientific academic perspective. So hopefully this works. So I just wanted to highlight again that we heard obviously from Matt saying how important the cryosphere and polar oceans are for the global planet, but just really to remind people that polar oceans are interconnected with the cryosphere and the rest of the planet through numerous ways. And as we've heard, what goes on there doesn't stay there. And hopefully I can highlight that. And I just wanted to put in some of the latest research that's coming out is really emphasizing that point, because we have things like sea ice loss, which we all are very familiar with. but that has real implications for how the ocean functions, and feeds back again for sea ice loss and other processes in the cryosphere. So things like opening of the Arctic Ocean, that loss of ice will increase air-sea gas exchange, and that can have implications for acidification, which we'll talk about. It can change the wind stress dynamics. It can change how the circulation patterns flow in the Arctic, and that makes a difference for how nutrient is delivered to the Arctic and to those primary producers, and that has knock-on effects for things like carbon uptake. And we're more familiar with the idea that albedo, if you get rid of that white ice cover, then we have more heat being absorbed into the oceans. But also things like permafrost melt. We're learning lots more in the last couple of years, really, about how the unlocking of that permafrost is allowing carbon to not only go back into the atmosphere through methane emissions, but actually the organic carbon that's going into the ocean is likely to amplify things like ocean acidification. And there's also lots of metals and things locked up in that soil, in that frozen ground, which are now being released and can also alter things like the nutrient budgets. So I'm going to just talk about warming, acidification, and freshening. So I'll keep going because it's not got a lot of time. But really just to highlight that the Arctic Ocean and the Southern Oceans are both warming, some of the most rapidly warming areas on the planet. So this is again from this SROC report that Matt mentioned, so 2019, so a couple of years out of date now, but it really just highlights how rapidly the two regions are warming compared to the global average. And in particular, what's interesting is in the Southern Ocean, actually the most rapid warming rates are occurring in the deeper ocean of the Southern Ocean. And that's really important when we come to think about how ocean circulates around our planet. So what is it like? What's the most recent update? So the State of the Climate Report for the Arctic for 2023 was released this year, sorry. And this is a map of August sea surface temperatures. And you can see that there's warming temperatures of up to 1.5 degree per year. And if you look at the long-term trends, so this top graph here, it shows how the sea surface temperature has warmed over the past 40 years. And you can see it's warming at a rate of about 0.5 degree per decade. And that's what the SROC concluded as well. So that trend is continuing over the last 5 or so years as well. But it is regionally different. So this is just an example from Baffin Bay. And you can see that overall, actually, it's increased. Its warming is a little bit slower, but actually it goes through periods of maybe a stabilized period and then rapid warming and then perhaps a more stabilized period. So it does depend where you are in the Arctic, but overall it is warming. And also seasonally, the warming is varying as well. And that's really interesting. This is a map of the sea surface temperatures and sea ice temperatures. So if it's got ice cover, then we're measuring the temperature of that top layer of sea ice. And if it's open water, then that's the sea surface temperature. And you can see that actually the red here is between 5 and 10 degrees above average, the long-term average. And that the biggest sort of red patches you see are actually in these winter months, which is suggesting that actually we're getting huge warming periods in the winter periods. So that's when we're expecting the sea ice to be there, and it's just not, the ocean temperatures are not allowing that sea ice to really form as properly as they should do. And not only are we seeing these kind of global trends and long-term trends, but actually that's manifesting into marine heat waves as well. So this is from 2023, and I think it's just really a stark, obvious example of how we can see where the marine heat waves are forming. So these are category 4, where it's really dark colors, and you can see the Arctic Ocean has a huge amount of category 4 heat waves, but also the Southern Ocean is starting to see those as well. And that's because of this increasing long-term trend, but also these extreme events that we're experiencing because of the weather patterns. So mitigation goals need to consider thresholds and polar oceans which are lower than global oceans for temperature. If we move on to freshening, so freshening, particularly in the Arctic Ocean, is driven by a balance between the inflow of freshwater, river runoff, ice melt, and more precipitation and evaporation compared to the outflow of water and ice. And what that means is we can track where the water is going, that freshwater signal, and where it's stored. And over time, this red line here is the observations of where sea ice, fresh water is stored in ice, and you can see it's declining here. And then this is the model of where we would expect that to go. So it's going to continue to decline in the future. And that fresh water is going into the oceans. You can see here this red line indicates that freshwater storage in the ocean has been increasing and will continue to increase. And that's really important for things like global ocean circulation. So we have the global ocean circulation, and particularly important is in the polar regions where we get this deep water formation, and we call it overturning. So there's salty warm water, it cools down and it gets really dense and it sinks to the bottom water. And as it does that, it moves down back into the Atlantic and drags up this warm water from the tropics up towards the polar regions again and circulates over and over. As we warm the oceans, but also importantly, as we freshen the oceans, as we add that fresh water, what we're doing is causing these to slow down over time. And actually, if you include that freshwater input into the model predictions, you see a 19% decrease in the Atlantic meridional overturning circulation strength, and actually a 42% decline in the Antarctic bottom water formation. And they're hugely important for things like nutrients, heat storage, oxygen, and carbon transport around the oceans. And that, as we heard from Matt, has important consequences for extreme weather patterns in the Northern Hemisphere, but also ice sheet loss in the Antarctic. So moving on to acidification, finally, oceans are becoming more acidic because they're taking up carbon dioxide from the atmosphere. They take up about 25% of the carbon dioxide that we emit as greenhouse gases. And that's causing the ocean chemistry to change, which results in a decrease in pH and a change in something called the saturation state of calcium carbonate minerals. And these minerals are really important for organisms with shells or skeletons to actually be able to form those shells and skeletons or dissolve away. And so here we've just got a map of the global oceans going through time from pre-industrial conditions in pH down into the future. And you can see where we start to get these emission scenarios is where we will end up in terms of pH and also aragonite saturation state here. So if we can stick to these low emissions, then we have much less of a change versus moving on towards these high emission scenarios over here. We're about here, which is really interesting actually, because it's the point now where the models start to diverge. So this is really the point in time now where we're actually going to make a difference, and we're going to start to see that difference emerging from historic records as we move forward in time. Which emission track we choose, this is the point now where we should start to see that divergence appearing. So the polar oceans are already experiencing much more corrosive conditions relative to these calcium carbonate minerals compared to the global oceans. So there's two maps here. The one on the left is pre-industrial conditions. The one on the right is for year 2020. This is a model data product, so it combines models and data products. And you can see that the red marks where you have this really low saturation state. And so this is where organisms with these calcium carbonate shells, these shells or skeletons, will struggle to form these and potentially be put at risk. And so you can see that there's been a really big increase in both the Arctic and the Southern Ocean of this undersaturated water. Acidification is a long-term problem. We know that this isn't going to go away immediately. It relies on long-term geological weathering processes to actually buffer that change. And so both the Arctic and Southern Ocean are predicted to kind of stick to the level that we get them at, depending on what emission scenario we make. And recovery will take tens of thousands of years. And even at low emission scenarios, so this is atmospheric CO2 concentration here on the x-axis and saturation state on the y. As we kind of go through time, even in this low emission scenario, we expect CO2 emissions to maybe come back down again. But if this was a linear system, what we'd expect is this saturation state to sort of bounce back up to present day levels as we reduce the CO2 concentrations. It doesn't. We move into a new state, and we're sort of stuck in this new state around the aragonite saturation state of 1. So we're actually going to reach a tipping point, a chemical tipping point. So we see this chemical tipping point, but actually we also know that biological organisms have thresholds that are above that chemical threshold, and we're already seeing those being experienced in the real world. So something like a pteropod is a small free-swimming snail. It's got these calcium carbonate shells, and you can see here on the left, this is what a shell looks like under a microscope. And you can see that these areas here are pitted away, starting to dissolve, and that's damage that we're already observing on these organisms in the polar oceans today. And we're predicted to see about a 61% reduction in suitable habitat for these key players of the polar oceans in the future. We're also expecting to see things in the Southern Ocean. So this was a recent paper mapping where ocean acidification is going to interact with marine protected areas. Sorry, press that too quickly. And all of these areas are going to be affected by undersaturated conditions under high emission scenarios. We can make them much safer places, much better marine protected areas if we stick to those low emission scenarios. So acting now prevents the worst. This is just a clear diagram from the SROC report where you can see the difference between sticking to low emissions or high emissions. I think it's quite obvious and self-explanatory there which one looks better, with red being not a good place to be. So ocean acidification is a direct consequence of CO2 emissions. Reducing those emissions can help minimize the risk of impact and help protect valuable species. So I'm going to finish there just with the conclusions that we really need to be acting now. I think there's a lot of evidence in the polar oceans to really sway us in that way. Thank you very much for giving me the opportunity to talk today. Thank you.
Thank you, Helen. That was a very comprehensive overview and really reiterated that message that these impacts are right across the system. I mean, that was the key thing. And also the other thing I took from that was we're at that threshold, that tipping point, which is scary, but also great that we're not quite past it, and it still gives us time to start acting. So thank you very much, Anne. That was great. We're not going to take questions yet. We're going to have a panel at the end with our in-person speakers and virtual panelists as well. So I'm going to hand over to our next speaker, who is Lawrence Mayer, who is senior scientist with the Greenland Institute of Natural Resources and the Global Ocean Acidification Observing Network Regional Hub Arctic. And Lawrence is going to speak to us on the Goan Regional Hub Arctic latest key findings, I believe. So thank you again for joining us, and over to you, Lawrence.
Yes, good morning, everybody. My name is Lawrence, indeed, and I live and work in Greenland, so I'll take you from a world perspective to Greenland. And I can very much relate with many of the things Paul said, like we are feeling climate change in Greenland as well, and it's a very important issue for you and for us. And I will speak a bit about our work around Greenland and like what's going on in Greenland. For Greenland, the ocean is really important. It's like an integral part of the identity of Greenland, especially because the economy of Greenland depends very much on fishery. And also, we have a massive coastline with fjords and bays all over, and we are a very large island. Consequently, we have a very large coastline. And not only Greenland itself cares about the ocean, also the world cares about the ocean around Greenland, because many things are happening in Greenland. You're all aware that we are home to the second largest ice sheet in the world, and we see that the ice sheet is melting actively, and the ocean is contributing very much to that. So what we try to do from Greenland is work with people all around Greenland and try to do measurements in different fjords offshore to try to understand what's really happening in our fjords and in our shelf seas, and trying to understand in which way, like, does changes in the ocean impact the ice sheet, and also in the other way around, because we really see that like the fjords and the waters around Greenland are really a gateway between like the Greenland ice sheet and the ocean, and they're really important in many processes. In one way, we see that warm water from the ocean moves inside the fjords and melts the ice sheet, and on the other hand, we see that larger and larger amounts of meltwater are coming from the ice sheets and impacting the fjord circulation, the shelf circulation, and also larger circulation patterns, as been highlighted by Helen. And also locally, this has a really large impact, and that's also something I want to highlight in my short presentation here. But first, I will take you to my own home. This is like a glacier in the in my own backyard, close to the capital of Greenland, Nuuk. And this, like just from the color of the rocks, you can see that this glacier has been retreating quite actively. And unfortunately, this is a story which is going on all over in Greenland. Our glaciers are retreating. And what's unique with many of Greenland's glaciers is they're like very much, as you can see, in contact with the ocean. Like we have Termini going, the water is flowing all the way to the fjords, and we have this marine terminating glacier where the glacier is in contact with the ocean. And since we live in Greenland, we actually go out winter and summer to take measurements in the ocean to try to understand what's going on, because climate change is not something which just happens in the summer months when most scientists come to Greenland to do some work. But we very much see that the winter months are very important, and like it's a privilege that we can go out and take measurements as well. And when we do these measurements for a long period, we have been doing it since 2008 in our fjord system, we can really see that like matching with the retreat of these glaciers, like it's very much driven by processes in the ocean. Like in the top panel, you see an overview of like how the glacier has retreated, and it's more than 5 kilometers in the last year. And below you see a graph showing like how the temperature has changed in like at 150 meters, because our fjords are several hundred meters deep. And we can clearly see that matching with the strong decrease, like in a period 2010 to 2014, there's warmer water who was in the fjord. And like warming is not a linear process. Like we have like the system is very much pulsed. Like so, it's some periods there's warmer water, and then we have had a colder period, and like now we're again in a warmer period. And that's also why like long-term measurements in our view are essential, because it's not just one time you can observe these kinds of changes. We need consistent measurements to observe this. Then when we look at like how does these melting glaciers impact the ocean, we need to look at like in which way like does the meltwater also enters in the fjords. And when we look at that, we see in Greenland and also worldwide that we have two types of glaciers. We have glaciers who end on land and where you have a river flowing to the ocean, but then we also have these marine terminating glaciers who go all the way into the fjord. And especially in Greenland, we have many large marine terminating glaciers. And what happens between them is like, for example, when we have this land terminating glaciers, like due to the large runoff, we have a very strong stratification, which limits like mixing inside these fjords, like and consequently nutrient concentrations like are low inside the fjords, because like nutrients cannot be welled up to the surface layer, and consequently productivity in these fjords is low. And this is something I've been trying to describe in my work, and actually I'm very grateful to like working with the local communities because it's through them that I learned that people say like these are dead fjords. So I think in that way it's also very important that we in our science more and more include people like from the different places, because they provide so much information about what's going on. This is something we see all over in Greenland, that these fjords are like very unproductive. This is showing chlorophyll, so we see very low concentrations of chlorophyll during the summer months. When we, however, look at these marine terminating glaciers, there's a very different process going on. In addition to some surface runoff, we see that meltwater percolates inside the ice sheets through holes and crevasses, and then it comes out at a deeper depth. And due to the fact that it's freshwater coming out in a fjord, we see very strong upwelling. And this here you see some of these crevasses and rivers where water is percolating inside the ice sheet. And then when it comes out inside the fjord, you see a very large upwelling occurring next to these glaciers, and you see plumes with water welling up. And these rivers are huge. They're the size of like some of the largest rivers in the world. And there's like very vigorous mixing occurring next to these glaciers. And these processes are really important regionally for supplying new nutrients and supplying really high productivity to the fjords. That's something we see also, again, in all glaciers along Greenland, where you see very high like phytoplankton biomass, and consequently also a very productive food web. And consequently, we see that like different fjords have different food webs, and glaciers play a really important role. And especially these marine terminating glaciers are really important for the high productivity in the fjords. Why do we care? We care a lot because this is where also a lot of the fishing goes on, and where actually our people live. Like Greenland is a coastal society, and most cities are based next to these very large glaciers, and people go fishing in these waters not only because it's because they live there, but they live there because there is so much like natural resources, and this is very much linked to these glaciers. But that puts also a lot of like threat on the lifestyle, because we see that these marine terminating glaciers especially are very susceptible to warming, and the glaciers are melting due to both high air temperatures, high water temperatures. And so the question is very much what will happen in the future to the rich marine ecosystems and also the glaciers themselves. So Greenland is very much in the forefront of climate change. So we are afraid that like many of the marine life will disappear when the glaciers will continue to melt. So, and also like globally, of course, the melt of the ice sheet has very large implications for sea level rise. So in many ways, like what happens in Greenland does not stay in Greenland and has both regional and global implications. And with this, I want to say Koyanak. Thank you for listening. And
Thank you, Lawrence. That was great. Really fascinating to see what's it's happening in Greenland, and just what it just made me think. I was kind of smiling to myself in the sense that I know in the UK media we often, anytime we hear about sort of changes in the system and lack of snow or glacier retreat, is usually to do with tourism or ski resorts and all sorts of crazy things like that. But once again, this is showing real impacts on communities and fisheries and the rest of the ocean. So yeah, really nice talk. We're going to have our final online science speaker now before we come back to people in the room. So finally, and once again, thank you. I have no idea what time it is where you are, but thank you for joining us. And we have Elise Hancock, who is Executive Officer of the Southern Ocean Observing System at the Institute for Marine and Antarctic Studies, and also part of the Goan Regional Hub, Southern Ocean. So Elise, over to you. Thank you.
Thank you, and thank you very much for providing me the opportunity to speak here today. And I'm speaking on behalf of the joint hub between SOOS and Goan for ocean acidification in the Southern Ocean. The Antarctic and the Southern Ocean is an ecosystem of global significance as a heat and carbon sink, but it's also a place that captures the imagination of people around the world as a marine ecosystem of wonder and as fertile grounds for fisheries and tourism. We really can't underestimate the value of the Southern Ocean and the Antarctic in the ecosystem services they provide and the disproportionately large role that it plays in the global climate system. The Southern Ocean is important for food security, with important fisheries like Antarctic toothfish and krill operating in the Southern Ocean. But it's also incredibly important culturally. People flock from around the world as tourists to visit the pristine Antarctic wilderness and to be able to experience the iconic wildlife that occurs in the Southern Ocean and the Antarctic, wildlife that contributes significantly to global biodiversity. But most importantly, the Southern Ocean plays a very important role regulating the global climate system in the heat and the carbon dioxide that it takes up. It also drives global ocean circulation. So with trying not to sound repetitive, what happens in the Southern Ocean doesn't stay there, and it impacts everybody around the world. Just a subset of these services have been valued very conservatively at being $180 billion annually. And this is just a subset. So in truth, the real value of the Southern Ocean and the Antarctic is much, much greater. But it's critically changing. We're already seeing warming, particularly at the mid-latitudes. We're seeing marine heat waves. And these heat waves have already been seen to have impacts on the primary production, that driver of the Antarctic food web. We're seeing freshening due to the melting of the ice sheet. And this freshening is already changing circulation in the Southern Ocean and therefore will impact global ocean circulation. We've seen record low levels of sea ice. Last year was the lowest record of sea ice extent on record. And this year's the second lowest. And this is starting to suggest that we're moving towards a new sea ice state. a sea ice state that will have catastrophic impacts to the Southern Ocean ecosystems. For example, we're already seeing breeding failure of emperor penguins, and this isn't just a once-off. A 6-year assessment is finding that this is becoming more and more common. And then ocean acidification. We already know that the Southern Ocean and polar oceans in general are very vulnerable to ocean acidification due to their cold temperatures and the increased absorption of CO2 at those colder temperatures. We're already seeing drops in pH. This is across all depths, as you can see on the left, and across all latitudes, as you can see on the right. But it's happening in combination with all of these other stresses. But ocean acidification in particular is going to have a very high impact. It's going to have a high impact across all depths and circumpolarly around the Southern Ocean. So I'm just going to step through a little bit more around ocean acidification and some of the impacts it is already and will continue to have on the Southern Ocean. So a recent study looked at the effect of ocean acidification on both currently established and proposed marine protected areas. No matter the area that we look at, we're seeing that ocean acidification will have a negative impact on the marine protected areas. Whether we look in this West Antarctic Peninsula area, what we're finding is ocean acidification will have an impact on both surface 200-metre waters, bottom waters, both on the continental shelf and off the continental shelf. And it will become worse the more CO2 emissions we have and those scenarios where we've got higher CO2 atmospheric levels. And then we see this around all of the Southern Ocean, in the Ross Sea Marine Protected Area and the proposed East Antarctic and Weddell Sea Marine Protected Areas. And it isn't just one species that will affect, but across the entire food web. It'll affect those important fisheries species, the Antarctic toothfish and Antarctic krill. It'll affect those primary producers, the drivers of the Southern Ocean food web. And then it will particularly affect benthic communities and calcifiers within the benthic communities in the Southern Ocean. Calcifiers require minerals like aragonite and calcite to form their shells and skeletons. And they're already and will continue to feel dissolution of those shells under future ocean acidification conditions. So I've already heard from Helen that the pteropods or the sea butterflies are already starting to experience dissolution. And this is particularly going to increase in Southern Ocean waters. But it isn't just the calcifiers. We're finding that it will impact those primary producers, the single cellular plants or phytoplankton. And the effects won't just stay within that single trophic level or single level in the food web, but it'll flow throughout the entire food web and the Southern Ocean ecosystem. So studies looking at the effect of ocean acidification on these phytoplankton have found that they're likely to shift towards a community dominated by smaller cells. And that will have flow-on effects through the Southern Ocean food web. For example, krill struggle to eat smaller cells, and we know that krill are a keystone species in most Antarctic food webs. It'll also affect the way the nutrients are cycled in these waters, and therefore impact the supply of nutrients from the Southern Ocean to global ocean waters. It's also likely to have an impact on the carbon sink in the Southern Ocean, as larger cells sink carbon better. So if we move towards a community dominated by smaller cells, we could find that the Southern Ocean isn't sinking carbon as well as what it currently is. So Southern Ocean will see the effect of ocean acidification, and the impacts of that will flow through all of the Southern Ocean food webs and all of those ecosystem services that the Southern Ocean provides. But it's not happening alone. It's happening in amongst with temperature changes, decreased in sea ice, freshening, and each of those different conditions will result in different winners and different losers. And what a combination of those changes look like and what the outcoming community will look like is still uncertain. And it's one of the greatest challenges for the Southern Ocean community. We need more observations and we need more monitoring of these ecosystems so we can understand how they're changing now, how they're likely to change in the future, and what that's going to mean for everybody around the world. So this is why SEUS released a call for action last year. so that we can address this chronic lack of observations, which is challenging our ability to both detect and assess the consequences of change in the Southern Ocean. It's more pressing now than ever that we have a sustained and coordinated Southern Ocean observing system. We need it to understand what's happening now. We need it to be able to inform what's likely to happen in the future so that we can best support policy and decision making, which is needed for the benefit of all of society. And this is why SUSE and GoOn have recently established an ocean acidification regional hub for the Southern Ocean, so we can bring together all of the community across all the countries, programs, institutes that are working on ocean acidification and the other changes in the Southern Ocean, so we can understand what's changing now, understand what's likely to change in the future, so we can best support that policy and decision making. Policy and decision making that we know needs to work towards climate mitigation, and we know needs to work towards that 1.5 degree target so that we can have a healthy Southern Ocean, which is required for the sustainability of all of society around the world. Thank you very much, and thank you for the opportunity to speak today.
Thank you, Elise. And yeah, definitely the call to action couldn't be more sort of urgent now in terms of us responding to that. And one of the things I thought when Elise was speaking is there's a concept, I'm sure you've all heard of it, called shifting baselines. You know, where we accept a new reality, a new normal, because we don't know what came before. And I think what Elise said about the chronic lack of observations and monitoring, we're really in danger in a few decades or maybe sooner of a new generation just thinking there's no ice, there's no penguins, none of this is going on. This is normal. It's not normal. We need to monitor this to say, actually, this is not how the system should look like. So I'd really like to echo what Elise was saying about we need to study this now so we can respond to it. So yeah, thank you to our science speakers online. We're now going to come back to somebody in person. We're going to shift slightly from purely the science to the science policy interface and science into policy. And well, I'll let Pam explain a little bit more. Pam Pearson is director of the International Cryosphere Climate Initiative. And Pam is going to speak to us on the cryosphere and the UNFCCC opportunities and challenges going forward. So thank you very much, Pam.
Yeah, thank you so much. And I'm going to, in just 10 minutes, really cover two things. One is sort of the context here for what we're talking about in terms of the polar oceans, but also a little bit more of the broader picture in terms of ocean and cryosphere science that we're looking at and trying to bring to the negotiators. And climate policy really has been evolving in this context. My own engagement actually goes all the way back to the Kyoto Protocol in the 90s. And back then, the thought was the Arctic is very far away. And it's something that, you know, is changing. It's the canary in the coal mine. But there was no real focus on the impact of things in the Arctic and then later Antarctica having any direct impact on the lives of people who didn't live there. And what we're seeing now is that what Arctic, especially Arctic indigenous peoples, were experiencing was simply the leading edge and the leading wave of the impacts from cryosphere, and those are spreading into the rest of the planet. When we look at COP29 and COP30 as sort of a whole, the troika, as it's called, in other words, the UAE from last year, COP28, this year, COP29, next year, COP30 in Brazil, they have all reaffirmed their commitment to the 1.5 limit. We're beginning discussions of 2025 NDCs really here. They're due technically in February of next year. Some have already put theirs forward. The UK, for example, has put forward a very ambitious NDC that would have 81% reductions by 2035. There will be some sort of a decision on the third periodic review under the climate convention. So this is the base convention. And I'm happy to take some questions on that, but that's basically where we say what the Earth system can have as safe limits. And it's been reviewed twice. There may be a third review. Certainly most of us in this community hope so. The other thing that I have to say now that we're seeing already here are challenges to science, challenges to mention of disappearing sea ice in cover decisions. It feels like there's been a politicization of places in the Paris Agreement negotiations that used to be immune to this. It seems to be creeping into that. COP30, it's in Brazil. It may seem to have no connection to oceans, but it does in many ways, in particular because if you think of what are identified as, tipping points, in addition to many of these being oceans-based and happening at the poles, the Amazonas is at the point of crossing a threshold into an extremely dry kind of system that may really have a huge impact on the planet globally. So there are some connections there. And this is a story of CO2. If you look at the past 3 million years between ice ages and non-ice ages, or as cryosphere scientists will say, glacials and interglacials, the CO2 levels went between 180 and 280, and that was very consistent. But this is where we are today. So we're way off the charts. And of course, that means that the systems of the world are responding temperature-wise, as well as in CO2. That is the global temperature, but what you're seeing in the Arctic is anywhere from 2 to 4 times higher. And one also has then the Antarctic and the HKH, the so-called third pole. And that has really led to an explosion of observations, findings, media coverage that especially over the year has simply been exploding in the scientific and media communities. And here are just some of the findings, again, more global. Record lows of snowpack in the Hindu Kush Himalaya. This has quite an impact on seasonal water availability for the people who live in those basins. There are catastrophic events. This is a glacial lake outburst flood that hit the high village of Tame, which is very well known to those who have visited Everest. Almost the entire village was really wiped out. There was record glacier loss, including in Western North America. In Sweden, where I live, they had the greatest loss ever observed in the glaciers there in 80 years of close observations. And this is the future that we're facing or not facing. If high emissions continue, this is the Great Aletsch Glacier, Europe's highest and largest glacier. It will be gone entirely almost by end of century. But if we can manage to follow very low emissions, we'll still lose a lot of ice, but there will be something left by the end of the century. So very stark choices there. And now moving to the poles, of course, you have Antarctica and Greenland, which both have been losing mass for quite some time now. Greenland is leading far ahead of Antarctica, but West Antarctica is beginning to get engaged now as well. And this has an impact on sea level rise. Hurricane Sandy, over 8 billion of the damage that it caused came from sea level rise, from glaciers and ice sheets, primarily from Greenland and glaciers. But the future is going to hold much more. This is just the beginning. And in particular, if one looks at this dotted line that IPCC AR6 identified as the level of sea level rise that might occur if some of these new models are correct that take into account ice properties in Antarctica, especially West Antarctica. These are the kinds of levels we're looking at. So this is Karachi with 3 meters, which probably is already locked in, honestly, but could take 2 or even 3,000 years to occur with very low emissions. It would be a very low rise. But on our current pathway, we could see these levels already early next century. And this would be 10 meters, which again, if you follow that dotted line, that's what you're looking at, certainly by about 2300. This is Miami in the US. This is Miami at 3 meters. And that line that you see is the Everglades dike that is meant to keep the water in the Everglades in, but by early next century, it could be keeping the ocean out. And then there are vulnerable communities. This is Dhaka, Bangladesh, at 1 in 3 meters. And most striking are countries like the Maldives. At 1 meter, much of the infrastructure will be wiped out. That could occur as early as 2070 on that dotted line. Their major airport is located in an area that is under 1 meter, but at 3 meters, essentially the country is gone. We've heard a lot already about Arctic sea ice, which has been declining and had really strong declines and almost a state change in 2007 and 2012, where it has stayed ever since. It looks now like Antarctic sea ice has undergone a similar state change and is now at a much lower value, and that has held now for a couple of years. So again, evidence that it's not going to bounce back. You can see this in 2024. And in the Arctic, looking forward to the future, even with very low emissions, we will probably see occasionally ice-free summers. It might just be a few days, though. But if we go into even moderate, let alone high emissions, you're looking at an Arctic that is ice-free for more and more months out of the year. And with very high emissions, you're beginning to approach ice-free states, except for the very depths of winter. And this would be an incredible change and an incredible blow to the peoples living in the region, but also globally because of the feedbacks from a much warmer Arctic. Permafrost, there has been a consensus paper that came out this year that really has said that the permafrost areas of the Arctic that green up during the summer, right? So they have been considered a sink even with thawing permafrost. That has now moved over. So we're now looking at Arctic permafrost being a net source of emissions. And that will continue to grow as permafrost continues to thaw. This is a global impact. This decreases everyone's carbon budget, but it also has extreme impacts on the peoples living in the Arctic, where you have infrastructure damage that can be quite extreme. And finally, we've heard quite a bit about polar ocean acidification and shell damage. But again, this is the IPCC SROC's projection for what we might be looking at by 2100 on our current emissions pathway. But again, I want to draw attention to many places in the Arctic that even on a low emissions trajectory are not going to be able to support shelled life, at least not year round. And so it's really, really important that we hold CO2 levels down. That's why I begin with that slide. The warming comes from CO2, the acidification comes from CO2, and it's set by whatever the peak levels are. Finally, we are seeing disturbances of ocean currents, and over just the past, I would say 6 months, the community, especially that studies the AMOV in the North Atlantic, it's been very uncertain that the fate of that particular ocean current. It would have extreme impacts on Northern Europe, but also, frankly, on Eastern Canada, where the amount of heat that is transported northwards would be much, much less. And there's a sense now among the scientific community that this is much higher risk, much more likely to occur already this century. And 40 scientists actually signed and turned over at the Nordic Council of Ministers meeting in Iceland a letter warning policymakers of the need to hold down emissions for this reason alone, let alone everything else. So in our 2024 State of the Cryosphere report, we chose, and you'll see it also on these toblers, to focus on 3 possible futures for the cryosphere and therefore the planet. Our current levels, which would lead to at least warming of about 2.3 degrees if NDCs are not radically improved. And that includes not just the NDCs to be presented next year, but we need to course correct on the NDCs in a sense that were presented already in Glasgow and that will start to be implemented next year. So the NDCs that people are talking about is 2025 NDCs. Those deal with the actions countries are saying they will take between 2030 and 2035. But we need to course correct before that. If we look at how quickly CO2 is rising in the atmosphere, that would take us to around 3.5 degrees by 2100, or CO2 levels well above 500, probably approaching 600. Again, that has dire implications for acidification. Or we can choose to turn and rapidly course correct and stay as close to 1.5 as possible. And then we have a much healthier Arctic and Antarctic for the peoples and for the ecosystems of the world. There are some signs of hope. The UN Secretary General has really taken this on and is trying to draw this connection between the Arctic, Antarctica, and the rest of the world. We have the Ambition on Melting Ice high-level group, which Germany joined earlier this week. The Central African country of Guinea will join next week. Some others may as well. Here again, AMI is meant to connect the countries and peoples of the Arctic and mountain regions with people who are affected, who are very far away and maybe have never even seen ice and snow, to make it real to them. So AMI consists not just of Arctic and mountain nations, but it includes Vanuatu and Samoa and Liberia, countries that understand now that they are affected by what happens in the Arctic. And this is one quote, again, it's drawing that connection from the Ambition on Melting Ice Declaration that was signed in 2020 at COP27 2 years ago. And again, this is possible. There are too many people in these rooms that are saying, 1.5 is out of reach. We may exceed 1.5 for some periods, but in terms of the definition of getting back down to 1.5, the very low emission scenarios have us peaking at about 1.6 and then coming down again by end of century. As a matter of fact, very low emissions has us down at 1.4 in 2100. That remains feasible, but it will require very strong emergency scale action. This is a huge challenge for humanity, but it is possible. We're just deciding not to do it. So again, we cannot negotiate with the melting point of ice or the polar ocean impacts of rising CO2 concentrations in the atmosphere. This gives all 5 of the dynamics that you see here and where their levels of threshold are. Some losses, though, are now inevitable and we'll need to adapt to irreversible impacts, but we can still choose how bad those will become. However, we also need to put forward that adaptation has hard limits, right? And when you hit those limits, it turns into loss and damage, a big part of the discussions today. And we really have these 5 years to course correct, and we need to look at 1.5 as a red line. So the State of the Cryosphere report, again, came out Tuesday this week. It's available online. We'll also have paper copies actually starting next week for those who are interested. So thank you for this opportunity, and hopefully together we can make a difference. Thank you.
Thank you, Pam. And it's so good to hear somebody talk about 1.5. As you said, it's almost like everybody's given up on that and talking about 2. And even in the introduction to the report, it's talking about 2 degrees, 3 degrees. So it's really great. I agree with you. We can do it. We need to be ambitious, but we can do it. We now have a bit of time for some Q&A for the panel. I believe the virtual panelists are still online, or are they coming back? Is that and Pam and Paul, I don't know if it's Pam, I don't know if you guys want to stay where you are sitting over here, or you could come and stand. Okay, I think because of the sound it's quite difficult to hear. What we'll do is, if there is a question, we'll invite somebody to come and answer it from the podium. Yeah, I think you're right, Pam, because I'm losing my voice shouting. It's really hard. Good, because I'm shouting loudly. So yeah, I'm going to open it up now to any questions, either to individuals or to the panel broadly. You'll probably not be surprised to know that I've got a few questions as we've gone along, but does anybody else from the floor want to chip in to anybody in particular? Yeah, sorry, if you want to, you want to come to the front? Yeah, thank you. And maybe if you ask a question, maybe introduce yourself and say you are as well. That's great. Thank you.
So hi guys online. You can hear me? Okay, my name is Christopher Imanefo. I work with a company in Switzerland called Oxyzen. And one of the key things I find that is missing in the conversation is that the emphasis is given on CO2 emission reduction as if that's going to solve the issue. In my humble opinion, that's only half of the equation. Why am I saying this? The issue is that there's a carbon load on the oceans, and we have seen what the effects are. So in addition to reducing CO2 emissions, we also have to reduce the carbon load. So what are we talking about? When we look at anthropogenic emissions and we ask the questions, how are these actually absorbed by the planet? 30% is absorbed by the terrestrial carbon sinks. Between 30 and 40% go into the oceans. And what the planet cannot absorb is accumulating in the atmosphere. So if we take 30% of the terrestrial carbon sinks, and if we are successful in reducing emissions by 50%, we still have 30% that is absorbed by the terrestrial carbon sinks, and we still have a carbon load on the oceans of 20%. So the only way we can reduce the carbon load is to also increase the terrestrial sequestration capacity on the planet. So we are kind of launching a slogan basically that says 50 down, which is good, but 60 up. So how can we increase the sequestration capacity of the terrestrial carbon sinks? That's the challenge. And this has to go simultaneously if we are going to achieve that. So it's not just emission reduction. Now, to increase the sequestration capacity on the terrestrial carbon sinks, it's not just planting trees. We have to rethink how we use land utilization, regenerative agriculture, one aspect, okay, moving away from monocultures. And there's a lot of things we need to think about. It's all the systems are combined. And we need to kind of move away from simplistic thinking and move more into understanding the planetary complex. And what we need at the end of the day is a planetary carbon balance. That's what we need to achieve. And so it's all hands on deck. So it's just a comment. We need to reduce the carbon load. And something else has to now come up. That's the terrestrial things. Thank you.
Thank you.
Okay.
Thank you. And yeah, I said comment more than a question. If anybody wants to pick that up and discuss, that would be great to pick up afterwards. Thank you. I'm just there are a few other questions that I've sort of have come in. One of them is around. I want to come back to you, Paul, and your openings. And one of the things you mentioned was the species range shifts. So species changing their distribution, species moving northwards. And I wondered, in terms of the Inuit Arctic conservation efforts, do you have some good examples for us in what you're doing in that area? But also, how can those of us who are non-Arctic, how can we support you and your community in your conservation efforts? I don't, yeah, maybe, if it helps. Yeah.
Hey, thank you, David. One of the examples I can speak of species coming up north is because of the ice is depleting so much, we're starting to see a lot more killer whales coming up. And they can decimate those species quite a bit. We're seeing more and more killer whales coming up, and they eat a lot of the whales that we rely on, especially on narwhal and beluga. So, and you have to understand, we don't contribute to climate change. We don't have huge factors. We don't have anything to contribute to global warming. So, but we are seeing the effects. We are the first indicators of climate change in the Arctic. So, how you can help? So it's beyond our control. So I don't know how I can say how you guys can help, because most of the factors are in the south, and the ones that are contributing to these emissions are from the south. So I can't really tell you. Thank you.
Yeah, thank you. Oh. Thank you for that. And I have to say also what you're doing from the Inuit community is having a massive impact anyway, as we said at the beginning, because your conservation efforts, but also the messaging. It's really important we go beyond us with our science and our reports to people like yourself saying we live this every day and we see it. So I think you're helping the general response amazingly by what you're doing, which is great. Thank you. I have another question, and this one I'm going to direct towards Pam. And really, what we're hearing today is that the change is happening incredibly fast, much faster than we originally anticipated. We have the IPCC reports that come out every few years, obviously, but is there any other way that maybe in between the IPCC reports we can collect things faster, collect data and scientific findings, report them quicker and communicate them? So if you want to speak to that, Pat, that would be great.
Yeah. Well, I mean, obviously, this is what we try to do with the State of the Cryosphere reports. We decided to start this with Glasgow because, indeed, we saw things changing so very, very quickly, both in terms of what we're observing, but also in terms of what the projections are. The science is getting more and more informed about what we can expect and some of the risks that humanity and ecosystems are facing. But an encouraging sign is that we're also seeing this being done. For example, WMO is putting out summaries on a much more regular basis. And so I think that the challenge is really gathering together the research, doing it in a way that assesses and can summarize it, but also I would say doing it in a way that policymakers and even the general public can try to understand, because this in some ways is very complex science. And if you're living in the Arctic as Paul is, this is really clear to you every day. And even where I live in Sweden, which is a bit more south, again, very clear what the changes that we're seeing. But if you are living, somewhere where it might, like sea level rise, and you're in Grenada, which has been undergoing some tremendous issues with flooding right now because of extreme weather, they don't think that that's connected to ice. But of course it is, in part. It's connected in terms of the higher sea levels. It most likely is connected to a warmer Arctic, causing some of these extreme weather events to take place, where you get disturbances of the jet stream. And those are the connections that we need to draw so that people understand urgency. Because one of the advantages of focusing on these regions is everyone understands that ice melts once you hit 0 degrees or 32 degrees Fahrenheit. That is a physical fact. And it's something that people can understand, and understand that if you don't want that to happen, you have to keep temperatures at -1 or, 29, 30 degrees Fahrenheit to keep the ice in its really natural frozen state. I've started to say that we need to understand that even the human species evolved on a planet with lots of ice. We've never existed in a planet that does not have that level of ice, and it's up to us to preserve it. Otherwise, we're going to be living in a very different planet.
Thank you. And actually, I've got a follow-on question. We're getting questions from some of our online participants as well. And it's to you, but also all the panelists. And the question is, how fast do we need to course correct? And the person who sent me the question says there still seems to be quite a strong focus on incremental change. So, yeah, I don't know, maybe Pam first and going back to our scientific panel. So, yeah, how fast do we need to course correct? And perhaps how does that happen? What's the most urgent priority? Maybe Pam first and then.
On this, we're guided by our emissions experts in IPCC, because IPCC came up with all sorts of different social and economic pathways that could lead us to a 1.5 consistent trajectory. Some of the ones identified in AR6 are already off the table because they're no longer possible, but others are. And so that immediate course correction, it involves, and I sometimes have a slide that shows this, it's really across all sectors, but a big focus now to 2030 on transport and on energy. They're the sort of low-hanging fruits. From now to 2050, really focusing on those as well as manufacturing. And then there are some that are going to be harder to address, like agriculture, for example, and methane emissions. Those are going to take more time, and they're sort of the focus after 2050, where we have carbon dioxide removal. So generally, that's what those pathways look like.
Yeah. Thank you. Yeah. No, he needs to leave. Yeah. Does anybody online want to come in on that as well? I'll take that as a no. I can't. It's quite difficult to hear in here, but I think Pam's covered that question fairly well anyway.
Yeah.
So okay. Another question that's come in, and one of the things we heard a lot about today is that the whole issue of ocean acidification and how serious that is in terms of impacts. Now, there is a UN Ocean Decade action, OARS, all around ocean acidification, and we've heard a lot from the Global Ocean Acidification Observation Network. So So the question here really, my interpretation of it is, how do we use this UN Decade Programme OARS to raise efforts, bridge gaps with the indigenous communities, but also bring the ocean acidification message to policymakers? Because I think it's quite technical, and there's a lot of biogeochemistry involved. It can be quite a difficult message. So how can we get that message across to policymakers and maybe even the public at large that ocean acidification is such a serious impact? So I'm looking at the panel online. I don't know if any who wants to jump in first. Otherwise, I'll just point to. So, well, should we get Helen? Do you want to go first on this, maybe? Just, in terms of that communicating this issue.
Yeah, sure. So I think what we have is the Global Ocean Acidification Observing Network has been around since 2012, and it's now got over 1,000 members across 115 different countries. So it's a brilliant network for really engaging the scientists across those efforts and bringing together the efforts. And what OARS has done, so this United Nations Decade Programme for Oceanification, I see it as kind of the map that allows us to use that knowledge and that network and that community of scientists to be able to deliver these messages to produce kind of the way that we want to be with the ocean's sustainability and acidification by 2030 and beyond. So for me, it's about really having a clear idea of what those messages need to be. And I think that's where Oars has had some really good ambition in terms of what their objectives are. We want to deliver policy messages, and I think we've been doing that quite well. So, for example, in the European region, we have been working with the Oceanification Alliance to work with European policymakers to look at how we can better integrate the oceanification monitoring and target discussion with the European policy frameworks that they have already, so that we can kind of, rather than make new policies and new regulations, we actually try and incorporate a lot of that into the processes that are already in place. And so that's been quite successful and has led to ongoing dialogues with European policymakers about how we can include oceanification into the sort of good environmental status that we have across Europe. So that's just one example, but in the interest of time, I'll let others provide some examples for talk.
That's great. Thank you, Helen. Lawrence, do you want to come in on this?
Yeah, I can shortly. Yeah, like it's a huge issue, of course, ocean acidification, but I know specifically for the Arctic, also for Greenland, like there are so many more issues than only ocean acidification, and like which are maybe more urgent, like the disappearing of sea ice, the changing like weather and winds circulation. Like it's much more urgent. So we try to like focus our message more on the things who directly impact the people's life than on like an issue which is much more complex also to explain. But like I agree, it's really good to try to like as much as possible to transfer this message to the policymakers. But I think there's so many issues going on that yeah, we should also not overwhelm people.
Yeah, absolutely. Thank you, Lawrence. And then finally, Elise, did you want to make any comment on this too?
Yeah, thank you. I just want to come back and I guess pull it back to these big questions like ocean acidification, which we have heard from Helen that even if it's not as urgent now, it's gonna stay impacting the oceans for thousands of years. So it's really, really important. But no single nation, program or institute can do this alone. So it needs GOON, it needs SEUS, it needs Oars to bring all the community together, to bring their understanding from their different regions, their different perspectives, so we can build an overall understanding. But things like SEUS and GOON also already have ready-made paths into policy. We can then bring that community together to bring that single unified voice, that unified messaging through into policy, so that then we have the best available science, unbiased, independent science that's coming from an international community, so we can form the decision making and the policies that we need. And so everyone around the world needs these decisions and needs this climate mitigation.
That's great. Thank you, Liz. And I think that's a good point to finish on. We're going to have to draw the event to an end, unfortunately. But I'd just like to say a huge thank you to our panelists, both in person. Paul's had to leave already, but thank you to Pam in person, and thank you to Elise and Lawrence and Helen for giving us your time. That's most valuable. Thank you to all those of you online who've engaged and sent in questions. And really importantly, thank you to the audience here. I know it's been really difficult with a lot of noise around, but I'm sure you'll agree it's been a really, really useful and valuable debate. So thank you very much. Enjoy the rest of your COP, and yeah, I'll see you around, I'm sure. Thank you.
Thank you for the honor. Thank you.
Yes, definitely.